Hey there, Precalc. I've got a new video for you. It's section 1.5. It's all about complex expressions, which is basically just another way of talking about what you do when you enter into a non-real number situation. So early mathematicians were kind of playing around with square roots at one point, and they said to themselves, we can't take a number times itself to get a negative number, right? A 4 times 4 would give you 16, but negative 4 times negative 4 would also give you positive 16. It seemed like nothing times itself would give us this, so anytime that we square rooted a negative quantity, we were just kind of stuck in the tracks and unable to move forward. Well, that was until I really don't know the history of complex numbers that well right now, but what I do know is that negative 16 was thought of as negative, or the square root of negative 1 times the square root of 16. And once we figured out that, hey, I can deal with that number, all I got to do now is sort of like name root negative 1 as something. And what they did was they called it an imaginary number. They called it I. So it's kind of funny that mathematics has this thing called imaginary numbers. But it's a true thing. So to make it so that it's a little more sophisticated, we called them complex numbers. So complex expressions, that's going to be the order for the day. All right, so you know the basics of where it comes from. How do we deal with it in the arena of algebra? Well, I'm multiplying a binomial expression, or a binomial times a binomial. Even though technically they're not polynomials, I'm just going to call them binomials. They work the same way. You can take 4 times 2 to get 8. 4 times 7i, I can just take the 4 times the 7, and then the I gets tacked on at the end. So plus 28i. Negative 3i times 2 is negative 6i, and then negative 21i squared, because you've got two i's being multiplied together. Now the interesting thing about this is that the directions state, write the expression in the form a plus bi, where a and b are real numbers. So our final answer needs to look like a plus bi, but we're stuck with an I squared. So what are we supposed to do? Well, going back to the drawing board, I showed you guys that it's defined that the root of negative 1, the square root, is equal to I. That's just a definition that was given to us right away. But that's the funny thing about definitions, especially if it's in terms of an equation. What if we did the operations that you normally can do to both sides of an equation? So I see I squared here, yeah? What if I were to take this original equation and square both sides? Yeah, interesting. So when you square a square root, the root disappears. So through algebraic manipulation, negative 1 is equal to I squared. So we can go back into this expression with the i's and rewrite 8 plus 22i minus 21 squared as, same thing here, minus 21 times negative 1. Which gives us positive 22 right here. Plus 22. Combine the 8 and the 22 and you get 30 plus 22i. So we successfully put it in the a plus bi format, and all is well in the complex universe. Let's try number 11. So on number 11, again, we're just kind of reviewing operations of polynomials within the context of imaginary numbers. So you can rewrite this as 3 plus 4i times 3 plus 4i if you want to. There's a square here. But in class the other day, I told you guys that there's a shortcut for it. Square the first, square the last, multiply and double. So 3 times 4 is 12, double it is 24. And it has to have an I on there too. Multiply that by I. If you don't remember the shortcut, just multiply it out like you normally do. All right, so at this point, you guys can do one of two things. You can go back here and say, hey, -1 equals I squared, and replace the I squared right away. So I'm going to do that. Actually, let's just erase the I squared and put a -1 in place of it. -1 is I squared. I took the I squared out, plugged in -1. So 9, this will be -16. 9 minus 16 is going to be -7, and then the plus 24i remains, times I. Now you can distribute the I. -7i plus 24i squared. And this is just like a continuous loop, right? You get an I squared, go back to the definition and say, I'm going to replace that with -1. So this will be -24 minus 7i. Next one in the textbook I want to check out is number 15. Oh my goodness, what is going on there? Yeah. So they want me to simplify I to the 43rd power. Yikes! Okay, but they're also giving us I to the -20th power. Yeah, just those two parts. All right, back to the drawing board. So we squared both sides, and we got -1 equals I squared. So this is interesting. It's giving us sort of a setup for I and I squared. What about all other multiples of I? So let's say that we had an I cubed. So this is your previous true statement. So this one's our first true statement. This one's our second true statement. What happens if we were to multiply both sides by I to create an I cubed? So multiply the right times I, multiply the left times I. Well, that gives us -I, or -1i, sort of a new identity. It's like, oh, I is root -1. I squared is -1. I cubed is -1i. I'm sorry, did I say -I cubed? I just meant I cubed. So we can continue that pattern. What would happen if we were to try to investigate the 4th power? So what if we said, hey, I want to just keep multiplying by i's. So multiply the right-hand side by I, multiply the left-hand side by I. Well, that gives you -1 times I squared equals I to the 4th power. But here's where it starts to loop. It starts to loop because it says, hey, we already know what I squared is. It's -1. So you replace that I squared with -1. It's -1 times 1. It's +1. Whoa. So 1 is equal to I to the 4th. And here's sort of I don't know if you'd call it the beauty of it. It's just kind of I would call it neat. All right? It's really neat how you start to recycle it back to the top when you say, Well, what's I to the 5th power? It's just I, and that's where we started from. So I to the 5th power is essentially equal to I. So here's what I'm saying. If you're given something like I to the 43rd power, what you can do is rewrite it in terms of, I don't know, you can rewrite it in terms of I squareds or I cubes. Let me just show you what I mean by that. I to the 43rd could be rewritten as I to the 40th times I to the 3rd. Because 43 is just 40 plus 3. And if you have powers of the same base multiplied together, you add the exponents. I know I cubed is negative 1i. And that's about as simple as I cubed goes. Also, I can take I to the 40th power and rewrite it as I to the 4th to another exponent. So 4 times 10 would give me 40. So it's I to the 4th to the 10th power is one way in which we can represent it. Now I to the 4th was a positive 1. So what's positive 1 to the 10th power times negative 1i? Well, it's 1 times negative 1i. It's negative I. By the way, that's not the only way in which we could, quote, break that down. What if I were to say I to the 43rd is equal to I times I to the 42nd power? See, that almost seems like an easier, strategic approach every single time, because what you can do is you can do everything in terms of I squared now. Because if it's an even power, then you can always represent it now as I squared to some power. So it's basically, what's 42 divided by 2? 21. And what that does is it says, okay, I squared is negative 1. All I got to know are the rules of what happens to a negative when you take it to an odd power versus a negative taken to an even power. Take negative 1 to an odd power, it stays negative 1. Take negative 1 to an even power, and it forces it to positive 1. So I don't know, guys. I mean, I would suggest doing whatever method works best for you. I mean, there's a lot of ways in which you can break it down into multiples of 4, multiples of 3, multiples of 2. So yeah, the world is your oyster. You can do whatever you want in terms of how to simplify these i's. I would say, though, that the most, keeping you at home would be to say, look, if it's odd, rewrite it as I times whatever the even power is, and then you can just stick with these. I'm going to do part B as well, because that one had a negative exponent, and I just wanted to kind of throw out there what I would do if I saw a negative exponent like that. I would look at it like this. If it's even, which it's a negative even number, I'm going to think of it in terms of I squared, and then it's going to be to the negative 10th power. You guys make sense of that? Negative 20 divided by 2 is negative 10, so I can rewrite it like that. I squared is negative 1. So what you can do now is say, isn't negative 10 for an exponent just mean put it on the opposite part of the fraction that it's currently on? Yes is the answer to that. So it's kind of like this is negative 1 to the 10th power, negative 10 power over 1, which equals 1 over negative 1 to the positive 10th power. At any rate, a negative number to a positive exponent, to an even exponent, will make it go to positive 1. So negative 1 to an even power creates a positive 1. So this is 1 over 1. It's 1.